Um, okay, please click continue on the prompt that you may have received from Zoom for recording. So once again, thank you for joining this workshop, the second session of our Intro to R workshop today. I hope you all were there with us yesterday as well. Today, I would like to start with a brief review of whatever we discussed yesterday, and then I will show you a few things, and then we will get started with analysis. So I will start scrolling down the slides, and if you want me to stop somewhere and have some question that you want to ask, please feel free to do so. Once again, just to remind you, in my mind, at least, R is a smart version of calculators. And if you have not been using R already, it is only because you have not been familiar with the interface of how to use R. But there are a lot of possibilities with R, a lot more than whatever you can do with calculator and Excel. And hopefully, yesterday I could convince you that it is um, not only it is a smart version of course calculators, and it is also worth your time to invest to try to understand how to use this smart calculator, because R understands biological data formats, lots of different kinds of visualizations. Heat map is perhaps one of the simplest among one of the simplest things that you can kinds of visualizations you can generate in R. You can generate variety of figures, and in a reproducible way. Since I have started doing my visualizations in R, I don't need to go to Illustrator or Photoshop, etc., to manipulate my figures. I can always program them, and then if my reviewers ask me to change something, add a point here or relabel this or that, or my supervisor would maybe ask me to change something, those things become very easy and to add to a script and just run it again. So for those reasons, I again recommend making your figures in R and not in Excel, etc. There are reasons to learn Python also, but of course we are not discussing that, so I'll skip that. And we discussed the 4 panes in the RStudio um, application, that when you launch it, by default you will see it. Of course, you can customize how things appear in RStudio by selecting or customizing, using all these options available in RStudio environment. RStudio is to R as Microsoft Word is to Notepad or TextEdit in Mac. So there isn't we are primarily writing our scripts. Here in this bottom left panel, if we ask a question, then the output gets displayed right away. While in the top left, we write commands that we can also save and run. So to run this, you can either press run or command enter on Mac, or control enter on Windows on a line, or you can select everything using command A the way you would in Microsoft Word or Excel or whatever else, and press command enter or run. Top right is our environment, where the objects that we create as we start with analysis or progress with analysis, they are reflected here. And in case you have forgotten, I'll just show you this image again. It's like it is helpful sometimes to think of things in physical terms. So the workspace or environment is like your real workspace or environment, which is empty when you start RStudio. So I will close it and I will start it again. So when we open RStudio, it will load the scripts from our previous session. And the environment is empty because their objects have been removed. By default, that's how R behaves. And we can load all those objects back again if we have saved them in our previous session. So I did save them, so I can load them using the R data file from the R data file that I saved yesterday. So we saved this R data file, and when we load it back again, we see all the objects from our analysis yesterday appear again in our global environment, our workspace. And those objects are like containers storing data. So we have two columns. First column is showing us the name of the object label, using which we can call that object in our later steps of analysis. And on the right, we have what that object contains. So DAT is a table with lots of observations of 14 variables. The others are single valued objects, so they are storing values. All of them are basically data, but here it seems like our studio calls one data and the other thing's value. That's okay. What else? We discussed these logical comparisons that we can perform in R, and some logical comparison logical operators such as not. An exclamation stands for not equal to, equal to. Two equals symbols or signs together make a logical operator, equal to or not, and operator, and the or operator. And then we also discussed functions, which are at the heart of programming in R. Functions are to R what buttons are, push button functions are to a calculator. In modern science, as we discussed yesterday, there are tens of thousands of different calculations you may want to perform with any given data type. Or you could perform. So instead of having a very complex keyboard like this, what we have is we spell out what would be perhaps the button labels if we were to design a physical calculator. So we have functions which are called as sum, product, mean, t-test for, to compare two sets of values and check if they are identically distributed or not, or things like that. We have a variety of statistical tests implemented in R. And as new methods are developed by some statistician or bioinformatician or whatever people like to call themselves, they would often implement them in R and provide packages for others to use. So packages are collections of functions where functions with related purpose, such as, for example, functions, a variety of functions meant for differential gene expression analysis of bulk RNA-seq data are implemented in a package called as EDGAR. The functions may be to make PCA plot, volcano plot, to perform normalization of counts matrix, and do hypothesis tests, those kinds of things. They are implemented in one package, all meant for bulk RNA-seq data analysis. And you have that. So when you want to analyze, or let's say, bulk RNA-seq data, you will install a package such as EDGAR or DE-seq2 or something else. And you will have now access to the functions from that package. And they are like the apps on smartphone. I hope you all remember all those discussions from yesterday. And also we discussed that these functions may require multiple inputs, and they may also give you multiple outputs, of course. The inputs may be, for example, to read a file, the input may be a file name, where the file is located, what format of the file it is. For example, are the values separated by commas if it is a tabular data? Are the values separated by commas, semicolon, tabs, etc.? Those kinds of things you can specify. And of course, we also met our good friend, the error message, yesterday. Just to again remind you that the error message comes in peace. It is not your enemy. So please don't get frustrated when you see it. Please try to read it, or maybe if you don't have time, you can always Google it. You will find help there. We discussed all these things, and now we can get started with reading our data. But before that, actually, I want to show you a couple more things. So yesterday we discussed a .r file in our script, which is what we call in our script. I also showed you this this document online, which is the documentation for a package for bulk RNA-seq data analysis. It is called as DE-seq2. Now, this kind of a document, as I mentioned also yesterday, the goal here is the goal in programming, and when we are writing our scripts, is to write it to be addressed to address it to a human being, and only the computer will of course execute it, but we should be thinking of our scripts as something addressed to a human being. And in that direction, people have actually literally gone in that direction. So this document, you can generate documents like this in R, and I will just show you how. But as you can see, the code, these are code, R code, and these are outputs from running R. These lines of code, they are or blocks of code, they are written out in this document together with the text that is intended only for humans to read. Now, this part of the text will be ignored by R if you run such a document in R, and R will know that these are code chunks that it has to run, and it will display the output. So in a certain way, you can think of it as if if you are reading a mathematical document or some computational literature, then you will find that there are equations or blocks of equations together with or embedded in between texts, or which are or text or paragraphs, etc., which are meant for humans to read. And also, of course, equations, they are all meant for humans to read, but they have a different meaning. So now in the modern computational biology, some people argue that um, the code should be treated like equations, and they have a new way of being interpreted, or like people interpret them differently, but anyway, they can be and should be used in text, just like equations. And that can be done using a feature or in R called as R markdown. So if you open a new markdown document, it will open something like this, and here you can see you can write text. There are, of course, some marks. It is called a markdown document because it uses um, I guess markups to identify what is a title. So this double hash or single hash or triple dash, they will be different levels of heading, and 2 stars enclosing something will mean that that thing has to be in bold, and you can have hyperlinks. And when you want to embed a block of R code, then you start with triple the stick marks, and then you write R, and maybe some other things if you want after this, and then you have a block of code between those 3 tick marks, and um, in curly braces you write R. So you have that option. You can generate documents like this, and when you press net, um, I will just let's say I will net it in my notes. So it will run it, and it will load something like this, where you have the output from that document, where you have this title and some text, and then code and embedded in between text, and then you have output from running the code, the figures, everything embedded in one document, and then it becomes really like a piece of literature. So you may want to make use of it if it helps your writing or whatever communication with your collaborators, etc. So just wanted to show you that. And another thing also to improve the our literary style here, is I think we can continue with this same script. If you have any question regarding how to load the data, or if you have trouble reading this data, we will get back to what this first line is doing later. But there is a package called as maggrator. You may or may not have it installed on your computer already, on your R already. And if you do not have it, I hope you all remember how to install it. Um, install.packages, there is a command called as install.packages. and you write in quotes the name of the package, magrittr. If you don't have it, you can install it, but maybe you already have it. So magrittr is a package which gives you access to certain um, operate. This is called a pipe. So by default, R does not have this kind of an operator. What this pipe means is whatever is the output of this thing, it will be passed on to the function afterwards. So if we write yesterday, someone asked, how we can maybe subset this table um, to get specific rows maybe. So we looked at um, a function subset, which will take a table and subset it based on some criteria. So we are giving this subset function a criteria that we want from this table, which has this column on gene ID. We want to extract just one row with the gene ID 12992. So if you want to, if you run this after loading this package magrittr, so magrittr provides you this operator, which is a pipe like real, I like to think of it as a real plumbing pipe, with water flowing through it. Instead of water here, we have data flowing through this pipe. So we have this function. The output of this is piped to this second function and placed wherever. So this dot here is where this pipe links to this function. So whatever comes out of this pipe is placed right here, which is um, the field where the subset function expects a data table to a object to be subsetted. So it expects in the first place the object to be subsetted. So when we run this, well, I have to set my working directory. It has given me an error because it is not able to find this file or directory in my current working directory, which is users/Krishna Chaudhary. So there, if we don't have this file is located at this location, as we again saw yesterday. So I will set my working directory to this location, and it will be a different location for you. So you have to do that. And I'm happy to answer that question in a minute, but let me just demo this function, this pipe operator first. So if we just run this much, then the output is 27179 observations of 14 variables. If we run this complete statement, then we have only one observation because this table was in one statement. We loaded it and we piped it to a subset function and we subsetted it. So that's how it works. And we will use this pipe in our next steps of analysis. Again, it improves reading. Um, um, by the original design of R was such that instead of having this pipe, people used to write composite functions like this. You would have subset, and in there you will write in subset you will enclose the second function, and then you will write this. But it became, quickly becomes very hard to read. It's like inside a function you have another function, and this is not how humans read. Humans read from left to right what is going on. Instead of starting from the center, you start reading from inside this function and then you go outside the function. So it becomes harder to read. So that's why people came up with this pipe. And there are different pipe operators. We will not discuss all of them, but maybe a few as we move along. Any question regarding whatever we have discussed to improve our literary style? If you cannot install magrittr or cannot find it on your computer, please unmute yourself and feel free to ask for help. Is this read dot table, is everyone able to read the table in their R session? So I will clear my R environment. I will also clear my console by pressing Control L. You can clear your console. I think this brush also works, clear console. And I will delete this part. We don't want to subset it right now. So I will delete it and I will run it. Now we have one object in our environment called as DAT, which contains information about, I will tell you what it has, but it has at least some gene IDs, lengths of genes, and then counts from a bulk RNA-seq experiment. And I will introduce the experiment in a bit. But first of all, if anyone needs any help with loading the counts matrix in your R session, I hope you all are working with me and also typing out and trying out the code. Once again, just to show you how to set the working directory, you go to session. We are setting working directory for this particular session. So we set working directory and you choose directory to wherever the file, this file, GSE 60450 is located on your computer. There are other ways to set it also, but you can explore it on your own time. Okay, let me check the, well, please do not hesitate from asking, if you are having trouble, you can also email, message me privately if you are a very shy types. That's okay. Anyway, okay, so there is a message. What does the header and the separator do? So thank you very much. Yeah, I'm sure that more people have that question. Thank you for asking. So in this file, let me open this file actually. So Gladstone chapters, workshops, 2020, intro or data analysis. So we have, where is the file? This file. So I will open it with text edit first. And let's see what is the content of this file. This file has one line at the top, which are not really the data values, but they are informing us about what the columns in this table represent. And then we have several lines or many lines, with values of for counts of genes, etc. So when we are loading this file, from using the first option, we are specifying the name of the file. The second option is specifying that there is one line, which is the first line, which is the column title. It is not a line, sometimes there you will have tables that you want to load, but the table does not have column titles. So in that case, the header you will specify as false, which will mean that everything is a line of, for example, let's set it to false actually. Let's see what happens. So when we set it to false, now we have one more line of code, and actually the first line, first line of data is actually not the data itself. It is assuming now that the first line is also data value. So gene ID and all this, names of samples. These are all names of samples. So that has become now the first line, and the column titles are absent. That is what is being told by us in this one line. Since that is not a correct description of the table, so we change it to true, and then R knows that the first line should be actually the column titles. How did you get the data to show as a tab? So there are two options. You can either click on the DAT in the environment, and RStudio knows where that happens. It means you want to see the data in a new tab. Alternatively, you can have a function view DAT. So I will not write this in my code because view DAT, this is something that we are uh, writing just for now. This uppercase VIEW view, and in parenthesis DAT. We are writing it interactively right now because we are still building our script. So when you are writing, what you want to analyze and how you want to analyze. Just you will flip through your pages like if it was a physical book. So similarly, you will want to check your data, what it has and if it is properly formatted or not. So you will maybe want to write those kinds of things in the console, but not save it in a script, because next time when you run it, maybe you don't want to run that line again. So you have to be judicious in what you write here or there. Of course, there are no rules, and nobody, if it's your script or which only you will see, then nobody will complain. But if it's a piece of literature addressed to other people, then maybe you don't want to write view here. Thank you for the question, Julia. Separator is doing, it is telling R that there are tabs in our document which are separating the columns, as we saw. Now it is, if we do just T, then it will assume that the letter T is the letter T is the separator. So, which is not true. If we do this, then it will say that different lines have different number of elements, because the T is not the separator. Slash T means a tab. T means the letter T. Slash N in R, or slash N means a new line. Um, so there are these special, um, for some special things, like how these things are internally represented. You will see that there is a, in the way these files are stored, with the tab delimited files are stored, there is actually, in the computer is seeing a slash T between the fields. It is only being displayed with a white space for us by text edit, but internally the computer sees a slash T there. So that's why we have to write a slash T. I hope that answers your question. Any other questions regarding reading the file? Those are all very good questions. And by asking those questions, you are doing all of us a favor, including other attendees. So I do appreciate you asking. I see someone is muted, so maybe they want to ask something. Okay, if not, then is everyone able to get this data loaded in their environment, and do they see? Are you all able to see these 27,000 plus observations of 14 variables? So please, a few confirmations will help. Okay, so good to hear that. So let's proceed with what we can do with this data. Now we have a data table, which is kind of long. It has 27,000 entries. Now, first thing, when we load a data, we may want to, again, just thinking of a textbook, when you get data, let's say in a register or a textbook, like a physical paper thing, then you don't just, look at the first page and start analyzing it. You maybe want to flip through the pages quickly. So similar kind of thing you can do in R also. So there is a function called as head, which will take an object as input, and it will display the first few lines of the table. So for example, here by default, head function shows you 6 lines, first 6 lines, but you can change that by specifying an option. You can ask for more than 6. You can ask for 10 lines. So it will display 10 lines, first 10 lines. And you will want to do that in some cases because, for example, maybe at the top you have only numbers in this column, but at the bottom you have a character or string type. String is something alphanumeric alphabets and numbers together, or other characters together. So maybe you have string type at the bottom. So you will want to know what your data is like before you implement some or implement some functions on, or run some tasks on those on a certain column of data, or the data together. So we want to just look at some of these functions, because we are discussing beginner stuff right now. Now I have told you about a function head. To view the last few lines, there is again another function, which is, I think you will all perhaps agree that this is quite an intuitive name, tail. So let's say we want to see only last one line. So we will say tail one. It may be also useful to, if you have very large data set, like with hundreds of thousands of lines. Here we only have 20,000, but hundreds of thousands or million is not unusual in modern times, and especially in genomics. So in those cases, maybe you want to, subset your table and run through the next steps of analysis while you are building your script. Just have a dummy subset of data for to build your script, and later on you submit it and go to bed, and wake up next morning for after R has processed 1 million lines. So for those purposes also, it may be helpful to use some of these functions. So there are a variety of use cases. Um, it's There is no limitation. Our imagination, I guess, is the only limitation in how we can use these functions. Any questions regarding these functions? Again, you may or may not choose to write this in your script. I am writing it here, and it is also there in this script that I have shared with you all. But that is only for demonstration. Now, if you look at this document that that the authors of this package, have written to demonstrate their thing, you will see that they are displaying a few lines of their tables, just because they want to demonstrate things here. So, well, it's always good to have them if you are trying to communicate certain types of things with your readers. Um, it depends on who you are writing for. Um, so there are other functions, utility functions, such as this, which are not doing any analysis, but they let you slice your data or look at what is there. So there is a function called as call names, which is going to give you the names of your columns. So we run this and we get the names of our columns. In certain cases, again, if you have millions of lines in your table, then loading a table in this new tab may not be the most uh, helpful thing to do, because it will take a while maybe to open a new tab and display 1 million lines. Or if there are thousands of columns, then again R will take a while to open this new tab. So in those cases, maybe you will want to use these kinds of functions to get some pieces of information. And you can always combine them. You can, for example, say call names, and you can say head. So you first of all run this function column names on DAT. This will display the names of the columns, and you pass the output of that to the function head, which will now display the first 6 entries, or the first 6 column names. Or you can pass it to tail, and it will display the last 6 column names. So again, you have those kinds of options, and this pipe is piping it from here to here. You may sometimes add this dot or ignore it. By default, whatever gets gets passed to the first option, or the first position. Another thing that I did not mention, but perhaps it is worth you knowing, when we wrote this function here, I explicitly spelled out, that this thing, this first entry or input, is the name of a file. The second entry is actually, or the second input that we are passing to this function is a header. The third is the separator. We don't always have to, be explicit in stating this. We can follow the positional order, by which I mean, if we don't specify these things, it will still work, because by default, R will assume that you are passing these things in the order that the function expects them. So for the first thing to this function read.table should be the file name. So if you have that as the first thing, then R will assume that it is the file name. Whatever, if you instead of this you have true, then R will assume that true is being input as the file name, and it will complain because true is of course a meaningless file name. Um, but it will assume that things are in positional order. And you can of course also combine the two strategies, so you can have you know the first is just like that, while the second one you have specified header is true and separator is this. So all these approaches work, and there is some flexibility around how you write your function calls. So when you read a document, an R document generated by someone else, you may see examples of things like this. In which case, if you don't already know what these positional arguments are representing, then you will have to check the documentation of the function. Any questions regarding these things that we have covered? That is the scope for our workshop today, folks. Trying out a bunch of functions, because that's all there is in R, functions and more functions. So once again, please feel free to unmute yourself at any point in time and ask if you have any questions. So we can also extract specific columns, entries in specific columns. Like let's say here we have lots of columns. One thing we can see is that these gene IDs. Let's see how R is how R is representing these gene IDs internally. Okay, we have a question. Let me check what the question is about.
Yeah, I'm still seeing an error when I try to use that. I think it's called pipe. Yeah, I see an error that says that it could not find that function. And I did install .packages magritter, I guess it's called. And
yeah.
I Googled and it looked like DPLYR might also, yeah, neither one of those. I'm still seeing this and I'm not sure.
Did you also run this line, library magritter?
Thank you.
So the thing is that installation will install it, but you also have to launch it, because again there are so many functions as you start with writing. Again, that's a very good question, and thank you for asking it. I'm sure other people may be also having this problem. Someone has to ask. Thank you for that. So yeah, so the thing is, you install lots of packages as you start using R. You install this package, that package, and if you again are by default, if it starts with all the packages loaded in your memory, then it will take a while to load, and maybe it will slow down your computer. So that is not a very efficient solution. So you have to load those things. You have to, at the top, you will in any script you will see, for example, this script also, if we see this, you will see that first thing is they are loading all the libraries that they will use. So they are saying library airway, which is I guess a package providing some data, etc. Then they are loading library txi meta. So that's how you will see our scripts. At the top, you will find that people often load all the libraries that they require in the next steps of analysis or throughout the script. After you load this, you should be able to access the pipe operator. So Nidhi, can you please share what you wrote in your, because so you loaded the library and it is still not working. So there are that information that you have shared in the chat is not by itself enough. If you can also write, what call names percent. So there is an arrow missing between your percent. The arrow is the pipe direction. The pipe can flow to the left or to the right or both ways. So you have to have this arrow in between, this greater than thing. So that should work if you have this thing also. And also I like to have space between my pipe operator and the function calls, and to the left and right, because again, it is meant for humans to read. Of course, the computer will understand, but this makes life simple. Any other questions? Those are all good questions. Thank you all for asking. I will proceed with the next thing, and again, of course, so someone is asking, when they are running head or tail, the console displays 2 entries per line. Can I get it to display only one per line? So you mean 2 columns? Well, you can stretch your console, in which case it will display more. So now if I do head DAT, it will display 3 because it has space to display 3. And these column names are very long, so they are taking space. Or you can have a larger screen monitor, or you can resize your screen itself, have smaller font sizes. Those are the ways you can, John, view more than 2 columns per line. Okay, let me give you another example. We will get to conversion of data types, so I'll skip that question for now. So I'm just look also having the chat box visible to me, so I'm responding to those questions in case y'all are wondering who am I talking to. Um, so first of all, let's extract one column of the data table, because that may be again another thing that we may want to do for our analysis, or here we are just trying it out. So dollar is the operator or the symbol which allows us to access a specific column, in this case, from our data table, or data frame is how they would call it, this DAT. So we can access, when we write DAT dollar, then it will display all the names of the columns, or we can type it out. So, or just press enter on one particular option. Either way works. And when we do this, all our gene IDs have been extracted into this new object called as gene IDs. And it says here int, which is for integer. And we can check the type of a particular data object by asking for its class. So class is a function which tells us the type of a object. There can be different types. In general, things numbers may not be integers. So in that case, we will just see numeric. They may be character values. They may be complex structures of data, and we will discuss things like that. They may be matrices, as someone was just referring to in our chat. So, but we know, in this case, we know that DAT, the first column onto gene ID, should not be integer, because they are IDs of genes, and they are numbers, and they are not numbers in the sense that we can add them, because adding 2 numbers in this case will have no meaning. You add 2 gene IDs, that has no meaning. So maybe we want to convert them to another data type, factor. So let's say we want to, not factor, we want to convert them to character. So we will say here that this is character. So we replace whatever is the content of this first column with this first column converted to character. So as dot character is a function that will take whatever is the input, it will force it to the character type. And when we run this, now the display is the same. If we view data then we still view the first column displaying numbers, but internally R is representing things as, so for example, if we do head DAT, um, then we will see that the first column, okay, here also it is not showing us, but let's run this line. Now I will copy this here again. So now gene IDs, and I will pass it using the pipe operator to the head function, and it is giving us everything in quotes, because the quotes mean that things are now character types. Now to convert from a matrix to a data frame, you will use a function similar to as.character. And Anthony, if you can take a guess what that function will be. And it's not, it will be something like this function. And maybe you can just start writing as in your RStudio environment, and it will suggest as what, as dot. Now you have all these options, and you will see that there is an option called as dot matrix. So as dot matrix will convert a data frame to a matrix. Now let's, since we have this question, let's just briefly discuss what it means to have different data types and structures. So I like to have this, I find this slide helpful. In real life, sometimes when we store data, sometimes a sticky note suffices. Sometimes we need a printer paper. Sometimes we need a task pad. Sometimes long scrolls. Sometimes we need a whole notebook, um, things like that. So similarly, in R, sometimes we need to store our data, a vector, an array, a linear order of numbers or characters. That is all we need, because that is our data type. Our data needs to be represented in one line sequence of numbers or characters, such as apples, oranges, butter, dry yeast, or numeric vectors. So we will then there will be one type of data that is called as vector. So for example, let's check what is the class of gene IDs. It is character. That means it is a character vector, a linear sequence of things which is character, which are all character. And then there can be numeric vectors, which we also saw, or integer vectors. Then there are also possibilities of data frames, such as this. Now this data frame, we can run class on, let's say, the first column of DAT. It is a character because we just converted things in the first column to character. Let's check what is in the second column. We can have, it says integer. So the first column has character, but the second column has integer. And the third column, let's say, what does it have? It is also integer. So the data frame can have basically a mix of different data types, or different types of things. So for example, character mixed with numbers, and different columns, we have different things. In the same column, we will have only the same thing. So everything in the first column is character, everything in the second column now is integer, and so on in the third and later on columns. In a matrix is another type of data structure in R. In a matrix, we can have multiple different types of things together. Sorry, a matrix only allows for one type of thing. So for example, if we convert it to a matrix, DAT, if we convert it to a matrix using this function as.matrix, dat as matrix. So let's see what becomes of DAT after converting it to matrix. So now we can again check or view DAT as matrix. So again, it visibly, when we view by eye, it looks all the same, but internally, how does R represent them? Let's check. So we can check class. DAT as matrix. Dollar does not work on matrices. So we will extract the first column, which we can also call by name. So these rectangular brackets or square brackets, whatever they call them, um, they take two values, the first value and the second value. The first value, the first place is for rows, the specific rows we want to extract, and the second entry is for the columns that we want to extract. Um, so here we want to extract the first column, and its class is character. Let's check what is in the second column. It is also character, because it forced everything to character type. That's how matrices are. Matrices store only one type of data, um, while data frames can store different kinds of data in different columns. So again, this is important. You want to check these types of things, and because when you just view by eye using these functions, class, or just view, then you may see everything being numbers, but sometimes you will also have white space after the numbers, which will make them character, because maybe when writing the Excel sheet, someone forgot and left a white space there, and those kinds of errors happen. So you want to just using these functions, identify what are the sources of error if you are seeing error messages, or just make sure that things are proper. Any questions regarding these things, these functions that we have discussed? There is another type of data which is called as list. List is a more flexible data structure, in using which, so for example, we can define list type. In this, we can have the first entry being DAT, or let's call it data frame is equal to DAT, and we can have matrix is equal to DAT as matrix, and we can also have a vector is equal to gene IDs. So now gene IDs is a list, and it has three different types of things. They are all, you cannot all combine them, in one table, because first of all, this last thing is not even a table. It is a vector. It is a linear thing. So if we write gene IDs, it will display a lot of numbers, or characters, in quotes. It is a linear sequence of things. It is not a table, but sometimes for some purposes you will want to collect all these things together. For example, maybe you ran some analysis and you got, you did, maybe let's say, variant calling in your data, and some whole genome sequencing data, and you found some variants in chromosome 1, 2, 3, but none in chromosome 10. So then what we will have in a list maybe will be names of chromosomes. So we will have chromosome 1 is equal to a table, chromosome 2 is equal to a table, while chromosome 10 is not is Na stands for not available or nothing, so you can have Na type. So Na is also a reserved word in R, which means nothing, so you can have that. So again, flexible data structures to give more power to you in doing analysis. And do you have any questions regarding these data structures that we have discussed? This was a bit of a digression from our plan of analysis, but again, it is all a bunch of functions that we will be trying out. So we have checked a few functions. Let's try a few others. Dim is for dimensions, dimensions of the data, DAT. Dimensions are 27,179 rows and 14 columns. You can also use functions such as nrow. Nrow is to display the number of rows and to display the number of columns. Now, I hope you all can guess that it will be called as ncol, or number of columns. So these are again different functions to take to take or to examine your data. how many pages in your book, similarly, how many rows in your table. You may want to have that information as you proceed with analysis. There is another very helpful or useful function, summary. Summary will display the summary of each column. So using the function summary, just the word summary followed by the object's name, we can get a summary of all the columns. We can view what is the first column. It is titled this gene ID, and it has this many entries, and they are all character type. The second column is length of genes, and it turns out that the median length of the genes in our table is 1976, and it shows us the mean and the first quartile, the second quartile, which is the median, and the third quartile and the maximum. And similar for other columns. So we can get a high level view of what is there in our data. And also, just to remind you, if you are an Excel user, you can also compare this with how things will be if you were maybe using Excel to do your analysis. Just to get this much information, you will have to perhaps do a bunch of manual stuff, to get these 5-number, 6-number summaries for each of your columns. So I hope again all of you are trying out these functions. How could you do the same thing per row instead of column? Now there are various solutions. How would you describe it? Again, as we discussed, if how would we describe a human being to do this? One way could be to say that we will convert this to a row. First of all, here it is a bit difficult to summarize for a row because there are different entries per row. But let's say we extract a part of our table, um, date subset, or just counts. Let's just extract the counts. So first two columns are information about the genes, and the rest of the columns are about counts. So let's extract the columns other than the counts, other than the gene information. So there is also this construct in R, which is a colon. So using a colon, we can generate a sequence of numbers. So if you say 1:5, it means that, give me all the numbers natural, or whole numbers between 1 and 5. We can also do this starting from -3, or a negative number to a positive number. Then it will give -3, -2, -1, 0, 1, 2. A minus in when extracting things from a table means that do not give me that particular column. So when we say -2 to -1, let's say we say -2 to -1, it means that we are telling R to delete the first two columns and give us everything else. So we are going to store everything else in this object called as counts. Now counts is all the columns of counts are numeric type only, or integers. So we can now, one way to do the summary per columns will be, first of all, transpose the the column. So I will pass it to a function called st, which stands for transpose, and then we will apply summary. But summary will be for too many things actually. So let's see what we get. I'll call this counts summary. Oh, I forgot a arrow here, a percent here. So now it is running a summary on 27,000 rows plus rows. So it is taking a while. It will, of course, give us the summary for all of them. Let me stop this. And I will, maybe what we can do is also extract the first few rows only. So by doing this, we are telling R to give us the first few rows and all the columns other than the first two columns. And then we get the count summary. So now count summary is for the first 6 rows, and we see the summary per gene instead of summary per sample. Once again, you may appreciate this pipe operator because now you can see that this pipe, it allows us to run things without having to store intermediate values in a new object. I mean, how many objects are you going to create? Not everything is meaningful to store. So things that are meaningful for you to store and maybe you will use later on, you store them in a new object name. Everything else, maybe you can just use pipes to process them through a bunch of steps. And once again, these parentheses, I like to have them to distinguish that these are functions and not names of objects. And by default, everything gets placed at the first position. If you want things to go to the second position, then you will have to pass on the input for the first position and have the dot at the second position, so that R knows that that's where you want to pipe to. But you can again look into all that in your own time. We don't want to get into details of piping. Any other questions? Those are all good questions. Thank you all for asking them. Well, that is because, so when someone did this, someone, instead of having -2 to -1, they had -2 to 1. And -2 to 1 will generate what? It will generate -2, -1, 0, and 1, but there is no column numbered for 0. So you will see the error, or will throw that error, only zeros are not, there in the table. R names all the columns starting from 1, so 0 is not meaningful. So again, you should also appreciate that there are these minor things that can lead to errors, and generally they are very minor things if you cannot catch them, and they are easy to troubleshoot. Any other questions? If you are getting any errors, those all errors are an opportunity for all of us to learn. So please do not, please share your error messages with us so that we can all learn together. Do not deprive us of that opportunity. I will, if not, if there is silence, I guess I'll keep proceeding with, things that I have planned also to show you all. So we have looked at a few functions to extract things from the table and, convert between types and check the types. Now let's load another table and look at some more types of data. So we will load another table, which I have also shared with you, phenotype info. It is a CSV file, which you may load using CSV or read.csv, or you can load it using read.table, where you will have to explicitly specify that the separator is comma and not white space. I'll use read.csv. Read.csv also by default assumes that there are column titles present in our file. So if we view phenotype info, it assigns column labels, and the first column apparently did not have a label. It was supposed to be the row names, but R is reading it as a column, which is okay for us for now. Anyone having problem with read.csv? Once again, you may notice that I did not explicitly write that this is file. Some people have that preference. They want to be explicit and write, naming their arguments. Some people don't want to do it. I am not, I don't have a fixed practice. Sometimes I am explicit, sometimes I am not. It depends on who our audience is and, what the purpose of our literature is or writing is. So we have this object now, phenotype info, and it has information about the columns in our, we have these weird named columns, right? MCL1.dg underscore blah, blah, whatever, uh, we want to now map them, let's say, to what information, um, what cell types or conditions those samples were assayed in. So for example, in this particular data, what we have is someone um, extracted tissue or some cells from the mammary glands of mice, 12 different samples, 2 cell types, and 3 biological conditions. The mice were female mice, and they were at different stages of pregnancy, and they were studying the expression of genes in the mammary glands. So, for example, one would expect that the milk proteins expression will be high in these samples, and we will find that. So this in this sample, if you analyze it, you will find that the expression of milk protein is the counts for milk proteins is higher in or the expression level of milk proteins is higher in the samples that are from pregnant mice. And second higher is in lactating, sorry, it is highest in the lactating mice. So things like that. But anyway, we are not going to go into the biology, but we have that information in this table. Now, the thing I wanted to show you using this table is this. Um, we have in the first column names of the samples. We have 12 rows, and each row has a different entry. MCL1, DG, HI, K, L, and then the next 6 are L, A, B, C, D, E, F. So these are lactating and sorry, not lactating, but these are cell types. So these are luminal cells from the mice, and these are basal whatever cells, which are not expressing or producing milk, or at least not committed to produce milk. I guess that is the biology of these cell types. But the thing to note here is that these entries are repeated, and these entries do not have the same meaning. From a statistical perspective, they have a different meaning than the first column. The first column are IDs of samples, while this cell type or the status, which are again also repeating entries, they are factor levels for statistical analysis. So for example, we may be comparing, when we are going to perform differential analysis in next steps, we will be comparing 2 groups of samples. And these are those factors that distinguish the 2 groups. So they have that sense or meaning in our statistical analysis. So there is a data type in R called as factor. And this data type you won't find in other programming languages, because R is meant specific, like R was designed by statisticians and meant for statistics. So statisticians have this data type factor, which is different from character type. Internally, factors are represented as numbers. They are level 1, level 2, level 3, but they may have labels such as B or L or pregnant mice or lactating mice. So we can convert, when we view, let's say, the columns. So let's say we want to view a particular column, X. Now X is all character. And similarly, let's say we want to check the column named cell type. So it is all character. We can convert it into factor, because maybe sometimes our statistical functions that we will use in next steps, we won't use them today, but someday or somehow, when you are doing analysis, you may need to have some data columns being represented as factors. So we can convert it into factor using a function which is as dot factor. So we can either do it this way. Again, we can say phenotype underscore info dollar cell type is as dot factor phenotype info cell type, in which case now phenotype info cell type, now it is a factor. Now you will note that the quotes are gone, and now it also displays the 2 levels of the factors. There are B and L cells. Now statistical a function for statistical hypothesis test or something, if it is designed to run to compare different groups in a certain way, then it may take an input using a factor type. So for your knowledge, this is another type of data in R. We have discussed factors, characters, numeric or integer types, and we have also seen um, the the logical types, logical factors. So for example, true, false. Here I'm creating a container. I like to think of it as a container, but C stands for concatenate in one array. So C true, false is just an array. We can have more entries in one array. We can create these kind of data objects manually also, besides loading from a file. So we can check the class of such a type. True, false, false, and this is logical. So those are some of the types. There is a comment from Deanna. If you want to clarify what you mean by top line C. Okay. Well, if you have a question, please feel free to again always unmute yourself. I'm happy to also. I'm keeping an eye on the chat also. So all cool. So those are some of the types that we wanted to discuss. We have discussed a bunch of things already. Let's see what else we have. Okay, more functions. Now let's say you want to extract unique types, unique values in a particular column. For that the function is unique. So let's say we want to find the unique status. The unique status is under which the mice were sampled or asset. So we can get unique entries in a particular column using the function unique. We can perform set operations such as intersections, set difference, using functions which have very logical names, such as intersect is to intersect certain sets, two sets. Set diff is to perform difference of sets, find values which are unique to one set compared to others. So you can do those kinds of things. I won't show those functions. Entry in sets. So for example, you can check if something is in something. So for example, we can check if the character version is in. So %in % is for in this set. So it returns true, which means that this string version is in this the set of unique values. Any other things that you want to talk about with regards to maybe sets? We have already looked at the subset function, so I will skip that subset function. Okay, now let's move on to doing some statistical things. Bharat, do you have a question? Oh, you did not try the subset function? So someone is saying that they did not understand as.factor, what it is doing. So factor is certainly a confusing data type in R. So once again, when we look at this table, phenotype underscore info, we have the first column. The first column is representing characters. It has, alphanumeric values, and also which is called a string. A string means something alphanumeric, data. So here we have alphabets and numbers together. So this is one type. In this column, we have MCL1, DG, HL, IJK, and these are unique IDs for each of the rows. These are not groupings of our data like our samples. While in this column, we have the cell types B, B, B. These are groups of samples. So these samples, which are again referring to our samples in our data column, our data has these samples, MCL1, DG, H, I, J, K, L, and then also L, A, B, C, D, E, F. So these are the samples in our data, and these are this table. It gives us information about what cell types are represented in those columns, and what status of mice were are represented in those columns. So now for statistical analysis, there is a difference between an ID of a sample and its group. ID is not going to be used for statistical analysis because ID is ID, but for when we are talking about groups, then some statistical functions in R, they will be meant for comparing two different groups. So we want to have our groups represented internally in R as a factor. So that is a factor type allows statistical functions to know that these are groupings of variables, groupings of things, data for statistical comparison. They are factors that differentiate groups of data points. Does that make sense, Bharat? So we were just converting it from this type to as dot factor. Now it is not relevant for our analysis here because again, we are not doing differential analysis today. But in our future workshops or in other places, you will find this factor type, and so it is good to know as a beginner. Because again, these are the basic things that on which um, our scripts are built. C is just C is again a function which you can use to create list of values, or sorry, a vector value, an ordered sequence of values. So for example, I showed true and false. So this, or we can have more things here. True, there are only two values, two logical types, true and false. So we can have these this sequence of true false, or we can have also sequence of numbers or characters, such as apple, and then boy, and I don't know, gamma. You can have vectors of different types, and you can create them manually also, besides loading data from a file. So I was just using this to demonstrate the fourth type, which is logical. So let's say we create a data type, logical type object, in which we have values true or false, and you can just write T also. T and F also means true and false are automatically fills in. So we have that, and we can check its class. We can check class of logical type. It will say that the class is logical. So this was just to show you that there are these different types. There are characters, there are numeric types of data points, and then there are logical types. And that is why I use the C. I hope that makes sense, Julia. We can also create those logical types instead of asking for, this by creating that manually. We could have asked phenotype underscore info dollar, let's say status is equal to pregnant. So now this logical comparison gives us true and false values, and this is all stored in which underscore b, or which underscore pregnant, if that's what we want to call it. Which underscore pregnant is for true false values, which is basically indicating which of the rows in our table phenotype info is pregnant, and we can check its class, and it is also logical. So just again demonstrating new things. Okay, let's move on to actually now doing some statistical things such as finding means and medians of things. Um, we can find the mean of a column. We already used the function summary. Summary gives us mean, medians, and lots of things, but we also have specific functions to find means. So for example, mean, um, we can find the mean of counts, dollar, the first column. So mean of that first column is 854.6172. We can find the median using the function median. Again, all these things are what you would perhaps put on a calculator buttons if you were designing one physical thing. So you can do median. And similarly, there are standard deviation. I hope you all can just guess what the name of the function will be. There are in R it is called as SD, but I guess there are some packages where you may find things called as sdev or std or other things. But in base R, these are think functions implemented that come pre-installed in R. Um, the function for standard deviation is called as count sorry SD, and we can take it for any column, so the standard deviation. We also have functions for variance, which is var, and what else
Hmm. Hmm.
is that a question? Someone was unmuted.
Oh, sorry. I think it was me. I was just talking to myself.
Okay, that's all good. No problem. um so again, there are a bunch of functions which you can try, and um I will show you some other types of things also. So for example, you can do string manipulations or string operations. For example, our column names kind of in this DAT thing, they are kind of complicated. Maybe we can simplify them, and maybe we can have them match what is in the first column of the phenotype info. So what we will do then to do that is we will use again pipe to get this column names of DAT. Let's say using column call names, we get the column names, and we will use a function called as extract from aggregator to get everything other than 1 and 2. So there are, I will, let's say this time I will use 3 to 12. So this displays the numbers, the column names of columns 3 to 12. Extract is extracting whatever comes from before. Extract will extract whatever is specified here. So I asked it to extract the 3 to 12 entries. Another thing I will just point out that this extract is a function that is implemented in several other packages. So if you load other packages, then they will override, you may want to explicitly name the package from which you are calling this function extract using this kind of syntax. So this is telling R that you want extract from the function from the package magreator, because extract is a common word. You can extract from a data table, but you can also extract from a list or some other things. So extract function is implemented in other packages also. In particular, I think tidyverse or which is a popular package, has this extract function. Um, so in those cases, you may want to explicitly mention a package name before you use a function from that package. And those two colons in between the package name and the function link the function to the package. And it performs just the same. It is only for R to know that the extract function from the magreator package is what you are referring to. So again, it is okay if you don't remember all this. I'm just demonstrating. You will have to practice in your own time. Goal here is again the grammar, not the vocabulary. You can build the vocabulary in your own time. Pretty much it's English anyway. So So we have the column names, and let's say we want to split them by the underscore. So we can see spot that after underscore whatever there is things we want to throw out. But there are several underscores, so actually split by, let's say, underscore b. So there is a function called as str split, which will split a string using a separator, which we will specify. So we will say split by underscore b or split at underscore b. So now it will split things, and it will give us a list of each character. Now it has been split into as many parts as it can be by at the this characters underscore b. Now it is converting it into this different type of object. Like now this is not returning the kind of data frame or data tabular type thing that we have been seeing, because each string may be split into multiple strings, substrings, because who knows how many times underscore b appears in a string, right? In all of this, it does happen for now that they appear, underscore b appears only once, but maybe it will appear 2-3 times. Let's say, for example, we split at underscore a, then what happens? Then some of them don't have an underscore anywhere, and while some have underscore a once, and so they are split into two substrings. So now it cannot be represented as a table. So by default, str split converts everything into a list. We want to split by underscore b right now. And then we can pass it to another function. I will pass it to a function called as lapply. Lapply takes a list and it applies a function to it. So we will say lapply on whatever comes from before, and we will define a function. So you can also define your own functions in R, and we will define a function which will operate on all of the list entries. So each of these 1 to 10 that you see here, and in this is one entry of the list, one element of the list. This is second element of the list. Each of them correspond to splitting one of the column names, and we have 10 entries. We will pass this to another function which we are defining using the function, and the functions, whatever comes in, will be called x, and we will ask it to return x1, the first from the thing. And then we have again a list of single entries, and we can unlist it after this, and overall we get the column names. I will respond to a question from Bharat in the chat. Perhaps you forgot this percent arrow percent, Bharat. If you have that, then the dot will link to this pipe. If you don't have a pipe before, then R will not know what to link here. Or you forgot this percent arrow percent.
Yeah, got it. Thank you.
Does anyone have any trouble understanding what this is doing? I did apply lots of functions here. So lapply, there is actually a whole family of functions in R which are called as apply families. Apply will take data objects which are going to be complex or larger data objects such as tables or data frames, or matrices or list objects, and they will apply a function to them. So this function, we are defining a function, just like there are functions inbuilt in R which we can call by different names. We can also define a function. We can say our user defined function. So we can define a function. Let's say here we will define a function extract first. We are defining a function, and this function we have to define two things. First of all, what this function will do, that we are defining inside these curly braces, and then we have to define how many things that function will take as input and what those inputs will be named. So we are defining an input. This could be named anything. It could be named, we will take an input which we'll call vector input. We can call we define this name. This is user defined function. So we are defining a function using the function named function. So this is a reserved word in our function. In parentheses, we define all the inputs. There could be multiple inputs, that our function will take, but it may not be, the case here. So we are defining a function which takes only one input. We can also have a default value. We can have a default value, say 1, 2, and 3. This is a vector input. And then we define this function. It is also reflected in our R environment as a function, which we have created, extract underscore first. And when we run extract underscore first, sorry, here we have to say vector input. The R is not defined. So this vector input will be available inside this function block defined by this parenthesis, this curly braces. And when we run vector input extract first now, it will display 1. What it is doing is it is extracting the first entry from this default input to the function, and it is displaying that. So we can run that function on now all our, we had 10 elements in a list. Each of those elements were a vector. So what we are doing is using this lapply function, we are applying to each of the list elements the function extract first. And the extract first is just defined above. So when we run this, we get the first element from each of the list elements extracted. And then the next function call is unlisting that and displaying as a character, everything as a character. If we just ran this much, then we will observe a list again, but the list will have only one entry because we extracted the first element and returned that as a list. Things are getting a little bit more advanced and complicated, but they are built on all the basic things that we have learned. Was that explanation helpful, Anthony? Do you have further questions? Please feel free to ask, because if you have questions, then it will also help me answer or explain it for other folks also. So I will let you think on it. But earlier someone asked, how do we do summary on each row? So to operate on each row, you can also use a function called as apply. So for example, let's say we want to apply something on the first 6 rows. So we will apply a function, let's say mean. Mean is defined in R, so we don't have to define this function ourselves. And it will, the first 2, we have to remove the first 2 columns because they are character or something. So what this is doing is it is taking a data table or data frame, and the data frame has 2 dimensions. One is rows and second is columns. So we are saying along the dimension of rows, apply the function mean for each of the rows, and it is returning 6 entries, 6 values to us, which are the means of the first 6 rows. And we saw these means above. Here, 140, 0.5833, 0, 2.25, 56.67. So just having a percent error this at the end will also not work, because you have to complete the sentence. You have to have, either you can run this much without the arrow percent at the end, or you can have something after this, because this means it implies that something will follow, and R is anticipating something. So I'm responding again to a question from Bharat in the chat. You have to complete the sentence. The last thing has to not have this arrow percent, because that means that the sentence has been, your statement to R or instruction to R has been completed, and now R can return something. If you just run these 3 lines like this, then it will of course not do anything, because it is waiting for more instruction in the next line. And you cannot also just start from migrator, because the dot here has to get something from before, that is also anticipating something from previous line. So this line is saying pass something here. If it just sees R just sees the dot here, well, where is the pipe input to that dot? So this is a new development in the past few years in R. The base R does not have this pipe operator. So recently, some folks have been trying to push for this. It is called especially the RStudio folks and the tidyverse community. And there is a split. Some people are more like originalists who don't like these pipe operators. They like to use, they will rather have a composite function where you enclose this thing in magritter and then you enclose whatever is magritter inside this str split. So they will have very long code, where you start reading from the center and move outwards. But of course, that is not a very tidy way of writing literature, I guess. So a community has adopted this. Lots of folks have adopted this pipes, and you will see them in your reading of our scripts. Let me show you now. Let's move on to doing some visualizations, making some figures, because that is another big part of our analysis. So you can make histograms using function hist to make a histogram. Let's say we want to make a histogram of column number 1 or 3, or just at dollar. So it seems that $DAT this is not numeric type anymore. Maybe we converted something sometime. It is numeric, so I don't know what is going on here. Dollar. I don't know what was going wrong before. So we can get histograms also. We can rename the axis. We can set limits on what we, what the axis limits should be. We can, for example, we can open the documentation for hist function, and you can see that it will take x limits, x limit, y limit. So I will look at my plot. It looks like, most of the values are not going to 100,000. So let's limit it to 20,000. Oh, not like this. We have to say C1 or 0, 20,000. So now what this is doing, it is telling the lower limit to be telling this function hist that it should set the lower limit to 0 and upper limit to 20,000, and we have to pass this together in one container to this argument xlim. So we have seen this function C before. Okay, well, that doesn't look, so maybe we will ask it to do more breaks also. Or let's do this. We will ask it to first convert it into log scale. So we will convert it to log2 by again piping it to log2. And then we will limit this. Let's not limit the axis now. Let's see how much where the axis goes. Okay, so this looks more reasonable. We don't have to limit the axis here to view the content of this histogram. We can rename the axis and limit the y-axis, x-axis, whichever way we want. We can add more annotations to this figure, but we won't go into details of visualization today. We have a workshop on data visualization using ggplot2 in R sometime later on in the year, I guess. Any questions regarding histogram function, what it is doing, how it is doing it? Of course, we could have all of this written like this also. We could have said log2. I like to have a line breaks often. So we could have written this whole thing like this also, which would give us the same output. But here the X and Y axis labels are gone because this hist function, it is not seeing the object's name. So it is just displaying a dot here because dot is the pipe input to it. So previously it had the titles and the access name, but now it does not. It is histogram of the input, and the input is represented with a dot. We can also make box plots, which are things, again, perhaps these things are not so easy to do in Excel, or certainly not possible in calculators, I suppose. So we can make box plots of many columns or one column at once. So let's try one column for once. Oh, why? $. I will just use this. So we have a box plot. It doesn't look very useful. So maybe we can again take log. We can do log like this. Know what is going on here. The box is not very well represented here. There should be a box. I don't know what is going wrong here. Maybe let me try another data column. Or maybe let's try log 10 here. Maybe that will improve things. I think something is up with my R session. Sometimes R misbehaves, maybe trying it again will. I don't know why the box is not coming on. Maybe I'll try to reload my session. I will just reload my session or restart R so that we can have all things. Okay, I have to load the library again and maybe set the working directory also. Not really sure why the box is not visible here. There should be a box. Oh, I guess it is because we did not, we took log, but there are 0 values in this. So we have to do something else. We will pass it to, first of all, add 1 to all these values. We will add 1 to all the values. Now here I am saying 1 plus the thing and then passing it to log. And now I think it should work. We should see a box. So now we see a box because log of 0 was not defined. So the box plot was misbehaving. But after we added 1 using the function add 1 to each of the entries. So it is passing on all these entries, adding 1 to them, and then plotting, taking the log of that and then passing it to box plot. And again, of course, you can write it more cleanly like this. Actually, there is even cleaner way to write it, but I will let you find it out using in your own time. There are more pipes which can make it even cleaner, but I will let you find that in your own time. So we get this function, this plot. We are extracting from the samples. We are extracting the counts for this sample, adding 1 to it, taking log, and then making the box plot. And again, we can limit the X and Y axis, just using the functions limit, ylim, xlim, all those kinds of things. We can always make scatter plots using a function called as plot. And we will give it along the x-axis. We want, let's say, we want the log of this. So let's say we say, there are different ways of saying the same thing, and you can choose what is going to be best for your purpose. I will say log 2 of 1 plus this. This time I will say things like this. And let's have a different different sample here, 1 plus deity dollar something else. And this will give us a scatter plot. Seems the counts are somewhat correlated, and we will expect that because they are counts for the same genes, also in replicate samples perhaps, or from at least from the same cell type. So we see the points scattered about the diagonal. Well, this is the function for scatter plot. Is there a function called scatter plot? It doesn't look like there is a function called a scatter plot. They just chose to call the function for scatter plot plot. Yes, we have ggplots. We will go to ggplot in the shortly, but we have a whole workshop on ggplot. So ggplot2 is a library where which is very useful for making all, if you have a visualization in mind, which you cannot describe using one word, such as, scatter plot or box plot or histogram. There are lots of functions, lots of visualizations that you will see in your papers or in literature nowadays, which are a combination of scatter plot with box plot, but also some heat map all on top of each other. So you can describe all that using a grammar, which is implemented in this package called as ggplot2, where the GG stands for grammar of graphics. We won't be discussing that today, but there is a workshop that we have. Yes, there is a way to plot multiple plots in the same plot, and there is a package called as patchwork, which you may not have installed on your computer, but I have it. So patchwork takes one function. So functions can also be stored in objects. So let's say I will store P1 in one plot, and this second thing I will store it in another object named P2 for plot 2. So I have two objects in my environment, P1 and P2, and let's see if I can combine them. So you just write P1, P2. I'm forgetting how you do use patchwork. I think you can use P1. Okay, so it perhaps works on only ggplot2 objects. So let's go to ggplot2 and I'm not sure if patchwork works with other things, but there are packages such as patchwork which will allow you to combine multiple plots in one panel, and then you can save. The way I do, my figures is I don't really like to add even A, B, C, D, for figure labels or what's sub labels or naming of the panels of the figures. I don't even like to do that using Illustrator or PowerPoint, etc. Whatever you are using, you can use packages such as patchwork or cowplot. Let's see if cowplot will do this. So you can plot in a grid. We can say plot grid P1 comma P2. Okay, now it works, I think. Well, perhaps it is. These are all meant for ggplot2. I'm not sure. I don't really use these base functions anymore, so I'm not sure why they are not working. But these packages you can use for mixing plots together. It's not coming to me off the top of my head why it's not working. Maybe you have to enclose them and see. I don't really know. Well, as I warned you, there may be some stupid answers. So this was one of them. Apologize for that. Okay, let's, I think this is the last thing we want to do, make some figures using ggplot2 library. So there is a library called as ggplot2. You may not have it installed. You don't need to install it right now. You can install it in your own time. It takes a bit of time. And I think you will have to install a package called as tidyverse. So tidyverse is a meta package kind of thing. It has many sub packages, and ggplot2 is one of them. So I will just use that package ggplot2 to demonstrate a few more functions from a few functions from them. These are not the functions which are the most useful, but this is what we have time to demonstrate right now. I encourage you very much to explore the ggplot2 package in your own time. So I will extract the first 1000 rows, pass it to the data field. Let's see how qplot expects, in what order it expects things. So qplot expects, I will say data is this, and then we have to specify what is going to be on the x-axis. So I will say along the x-axis, I want, let's say log2 of 1 plus this thing. So ggplot2 is designed to search for the names that we give in the x and y things in this data frame. So we don't need to say $DAT like we had to do with the base R functions. And we can say along the y-axis, we want, let's say, log2 of 1 plus something else, make it DJ thing. And qplot will also make this plot, but the plot looks a little bit nicer. First of all, of course, there are fewer points because I extracted 1000 rows from the top. But there is some design at the back, in the background, the gray. If you see plots in your papers where there is this gray background, I think that is a signature of ggplot2. You can also overlay colors on it. For example, you can ask color is equal to length, or let's say log length. Log2 of length. So now it will color by length, and we can see if there are any patterns. For example, are longer genes having more counts in general? In this figure, it is not so clear. So let's actually change it to length greater than, let's say, 4000. So now what it is doing is, first it is comparing all the lengths against this, performing this logical comparison with 4000. And then there are two categories, false or true. Some genes are greater than 4000, some genes are shorter than 4000. So here it seems that the shorter genes are indeed having fewer counts, and there is an increased level of fragment raw counts, for longer genes. So now maybe we need to normalize our data, and those kinds of exploratory analysis insights we can gain from, our data visualization. So I do encourage you all to get on board with ggplot2 also, because that will really help you deep dive into your data and explore it in many ways. Now, I will not, there are many things which you can do in R. As I said, we cannot demonstrate all of those things, but I will demonstrate, let's say, a t-test. Let's say we can perform a t-test. So I will create a subset of data. I will extract 2000 rows, and now we can have small genes. We can create a column called as so what here I have done is added a column called as gene type to our data subset, where small genes are the ones which are shorter than median of the lengths, and the long genes are the ones which are greater than the median length of the genes in our table. And we are comparing these two sets using that function t-test. If the the lengths are identically distributed, or sorry, if the counts for this sample are identically distributed for long and small genes, and it turns out that they are not, which is again, reflecting what we saw in this figure, that longer genes have higher counts. So you can perform these t-tests, or there are a variety of tests implemented in R, which you can access just with the name of the functions, and a lot of power to you. And there are, many such tests, and you should look into that. You should not just blindly run a test. You should look into what these tests are doing, and if necessary, you can check the references. It seems that there is no reference here, but generally R will also have a reference, a bibliography kind of thing, to point you to where you can read about t-test. T-test is a very common test. So here there are no descriptions, but it is perhaps not appropriate to run t-test on this data because the data is not satisfying the assumptions of t-test. So maybe it is not appropriate here. I just demonstrated it, but you should read what is going on. And based on the value from from a certain analysis, you can use constructs such as if, else to do more tasks. And here I have just written print statements. Print the count depends on gene length, but you could have more computations in these blocks separated by the parentheses. And finally, also there are looping constructs such as for loop, which you should again be aware of and explore in your own time. So these are the many things that we had planned for this workshop. I will let's see if I have some things to point to in from our slides. I have already pointed to this. Yeah, this and we have also discussed data structures. Just another thing to point out is that sometimes as in real life, we need different kinds of notebooks to save different kinds of data. Similarly, in these packages that we will use, they will come with their own data structures implemented, such as, for example, the EdgeR package for bulk RNA-seq analysis I mentioned. It comes with a data structure called as DGE list, which is based on the same basic structures of data frames and lists and vectors, but users have defined a new structure in which you can you can read on it in your own time. Surat has its own data structure object, so you can look into all those kinds of things, and we will encounter them in our upcoming workshops. So I thought I should let you know. I have shared with you some files and some tasks which you can try out, but I think you should just jump in with your own data and test these things. We will be very grateful for your feedback. This workshop design would not be possible without your feedback. Every time you give us some feedback, I try to improve things. So please do provide feedback. Your feedback helps us improve our workshop designs. And there are more kinds of graphics that you can generate, which you can look at in your own time using explore from our graph gallery, where there are a bunch of fancy visualizations which you can generate just with a hit of button, in R. So please do look at it. And then there are more packages for you to explore, and we have upcoming workshops. And I will like to now conclude with these statements. I hope I was able to convince you all that R is but a smart version of calculators, and you already know a lot about R than you may think you do. And the error message, it will come again and again, but it comes in peace. Please just try to write your scripts as addressed to human beings as pieces of literature. And if you get stuck, well, Google is always, knowledge is available on demand, and you can always Google or ask questions on Slack, at UCSF Winton channel or Gladstone Bioinformatics channel or other places. And I hope things were useful, and you will integrate. I hope you will start integrating R in your research right away. If you have collaborators, ask them for the scripts where you can make minor modifications, run them again, or just ask them to share scripts which you can read as pieces of literature, and also get on board with learning more functions. That is the best way to learn, I would say, to read scripts from your collaborators who are doing analysis for you, or downloaded from papers on GitHub. You will find scripts associated with papers that you may be reading. Just read them, and those things will help you. And if you have any further questions, I will be happy to take them now, or feel free to log out. And thank you for your time. Okay, so most folks have logged out or left the call. So sounds like there are no more questions or folks are busy. So shall we end it also?